A spacecraft can be carefully designed, correctly launched, and faithfully following its instructions, yet still miss its destination because two teams disagree about what one number means. That is the story of NASA's Mars Climate Orbiter, a real engineering case in which a unit conversion failure changed the predicted path to Mars. I want to walk through what happened, what the investigation actually established, and why this was not simply a careless typo. The deeper problem was an interface between people, software, contractors, and engineering assumptions. Mars Climate Orbiter launched on December 11, 1998, as part of NASA's Mars Surveyor program. Its job was to study the Martian atmosphere, weather, dust, and climate while operating in orbit around Mars. It was also intended to support communications for other Mars missions. The spacecraft spent about 10 months traveling through space, and during that journey, its ground teams continuously tracked its position, calculated its trajectory, and planned the small adjustments needed to guide it toward Mars. The spacecraft reached Mars on September 23, 1999, but when it approached the planet, it was on a path far lower than planned. Communication was lost as it passed behind Mars, and the spacecraft was never heard from again. NASA's investigation concluded that the trajectory had taken Mars Climate Orbiter through the upper atmosphere at about 57 kilometers above the Martian surface, instead of the planned altitude of roughly 140 to 150 kilometers. At that lower altitude, the spacecraft could not complete its intended orbital insertion. The exact final physical sequence was not directly observed because contact was not recovered, but the trajectory error was established as the central technical issue. The specific component at the heart of the case was not a large engine or a dramatic structural part. It was the data describing small forces created by the spacecraft's attitude control thrusters. These thrusters were used to adjust the spacecraft's orientation. Whenever they fired, even briefly, they produced a tiny push. That push mattered because spacecraft navigation is built from very small changes in velocity, position, and direction. Engineers on the ground needed to account for those forces while estimating where the spacecraft really was and where it would go next. The relevant quantity was impulse. In simple terms, impulse is force applied over time. It tells you how much a firing changes an object's motion. In the metric system, impulse is measured in Newton seconds. In the traditional United States engineering system, it can be measured in pound force seconds. Those are not interchangeable labels. 1 pound force is approximately 4.448 newtons, so 1 pound force second is approximately 4.448 newton seconds. The number can look perfectly ordinary in either system, but the physical meaning changes by that factor. The Mars Climate Orbiter investigation found that one ground software data file reported thruster impulse information in pound force seconds, while the navigation software treated the values as if they were already in Newton seconds. The conversion that should have happened at the interface did not happen correctly. That meant the navigation team was working with an incorrect estimate of the small forces acting on the spacecraft. This is an important distinction. The entire mission was not simply using the wrong unit everywhere. The problem was that one part of the system used one convention and another part assumed a different convention. The numbers crossed from one software process to another, but the unit meaning did not cross with them. In engineering, that can be more dangerous than an obvious wrong number. A value such as 10 may look reasonable, whether it means 10 Newton seconds or 10 pound force seconds. Nothing about the digits announces that the interpretation is wrong. The issue became harder to see because the thruster impulses were small. No single firing necessarily created an obvious, immediate contradiction. Instead, the incorrect force information affected the calculated trajectory over time. To understand the mechanism, imagine trying to guide a boat across a large lake while accounting for every tiny push from the wind. If your wind sensor reports a force in one unit, but your navigation program interprets it in another, each individual correction may look minor. The boat does not instantly turn around. But if the same misunderstanding is repeated, the predicted position and the actual position gradually separate. In deep space, the same principle applies, except the distances are enormous and the target is moving through a precise gravitational environment. Mars Climate Orbiter was not guided by one command that said, simply, go to this point. Its flight path depended on a continuously updated estimate. Ground teams combined tracking observations with models of gravity, spacecraft motion, planned maneuvers, and smaller forces such as attitude control firings. If the model receives incorrect force data, its estimate of the spacecraft's state becomes biased. That bias can influence later calculations, including how much correction appears necessary and where the spacecraft is expected to be at the next important event. The error did not need to be large compared with the spacecraft's total speed. It only needed to be large enough to matter at Mars orbit insertion. This is one of the most difficult ideas in spacecraft engineering. Precision is not just about measuring the major forces. It is also about consistently accounting for the small ones. A spacecraft traveling between planets is mostly coasting, but coasting does not mean the path is simple. Gravity from the sun and planets shapes the trajectory. Small engine firings adjust it. Attitude control activity can introduce additional forces. Radio tracking estimates range and motion from Earth. Software models turn all of that information into a predicted path. Every input has a place in that chain, and every interface is an opportunity for a mismatch. The most common retelling of Mars Climate Orbiter is that NASA forgot to convert pounds to kilograms. That version is inaccurate and points to the wrong physical quantity. The issue was not primarily a mass conversion between pounds and kilograms. It involved force impulse, pound force seconds versus Newton seconds. That detail matters because it shows how easily a public explanation can flatten an engineering failure into a slogan. The real case is more precise. It involved a ground software file, small thruster forces, a unit convention, and a navigation process that did not catch the disagreement before arrival at Mars. Another common view is that one programmer made one mistake and the entire mission followed it. The investigation points to a broader systems problem. A single incorrect assumption entered the workflow, but the reason it mattered so much was that other layers did not reliably challenge it. Requirements, software interfaces, test procedures, team communication, trajectory analysis, and mission operations all formed a chain. The chain did not contain an effective barrier against the unit mismatch. This is the missing angle. A unit is not merely a formatting choice attached to a number. A unit is part of the data. If a software interface sends the value 5, and does not clearly encode whether that means Newton seconds or pound force seconds, then the interface is incomplete. The program may run perfectly. The calculations may be mathematically correct. The result can still be physically wrong. This is why unit failures are so persistent across engineering. Computers are excellent at arithmetic, but they do not understand the physical meaning of a number unless humans define it. A computer will not stop and ask whether 5 is a force, a mass, a distance, or an impulse. It will accept the value that arrives and apply the instructions it was given. The Mars Climate Orbiter case also shows the risk of contractor boundaries. NASA's mission involved teams working across organizations, including the spacecraft contractor and the navigation operation at the Jet Propulsion Laboratory. Different groups can develop sensible local practices. One team may use English engineering units because that convention exists in its software or hardware environment. Another may use metric units because that is the standard for its analysis. Inside each team, the numbers can appear normal. The failure happens at the boundary. If the boundary is not explicitly documented, tested, and monitored, every team can believe it is using the correct value. This is not an excuse for the error. It is an explanation of how a small mismatch can survive inside a sophisticated program. The NASA Mars Climate Orbiter Mishap Investigation Board identified the unit mismatch as the root technical cause and also described contributing process and organizational factors, including inadequate communication and weaknesses in verification and mission operations. That evidence supports a systems conclusion, not a claim that one individual carried the whole responsibility. Publicly available findings do not justify inventing a dramatic confrontation, a hidden warning, or a single villain. The record is more useful than that. It shows an interaction between a faulty data convention and a process that did not provide enough independent protection. There were also opportunities to compare different views of the trajectory. Tracking data, predicted motion, maneuver results, and spacecraft performance can provide independent clues. But an independent check only helps if the teams know what quantity they are comparing and in which units. A beautifully designed graph can still be misleading when its inputs are mislabeled. The lesson is not that every number must be manually inspected forever. The lesson is that important interfaces need checks designed around physical meaning. A robust system could attach units directly to data types rather than treating values as unmarked numbers. Software could reject an input when the expected unit does not match the supplied unit. Conversion could happen in one controlled location instead of being assumed by multiple teams. Independent navigation calculations could use separate methods and compare results before a critical maneuver. End-to-end testing could send representative data through the same path used during the mission, rather than testing each piece only in isolation. Analysts could also compare an expected physical range against the received value, although a factor of 4 error may not always look absurd when the underlying force is small. These measures are not glamorous, they are interface discipline, and that is exactly why they matter. Engineering safety often depends less on a brilliant final calculation than on preventing two reasonable people from assigning different meanings to the same input. I also want to be careful about the boundary of the evidence. We know the spacecraft's communication was lost during its Mars arrival sequence. We know the investigation identified the unit mismatch in the small forces data as the root technical cause. We know the trajectory was much lower than planned. We do not have a recovered spacecraft record showing every physical event after communication ended. So it is more accurate to say the evidence points toward the spacecraft entering an atmosphere regime it was not designed to traverse during orbital insertion, rather than claiming to know every final detail. That distinction is not just cautious language, it is good forensic practice. A strong investigation separates what was measured, what was calculated, and what was inferred. The measured facts include the launch, the tracking history, the data handling process, and the loss of communication. The calculated facts include the reconstructed trajectory and the altitude estimate. The inferred conclusion concerns what happened after the spacecraft reached that low path. Keeping those categories separate makes the case stronger, not weaker. Mars Climate Orbiter is valuable because the failure looks deceptively simple after the fact. Once someone identifies the missing conversion, it is tempting to say the answer was obvious. But before the outcome, the numbers were moving through real software, real teams, real schedules, and real assumptions. The system did not announce that the interface was wrong. It allowed the mismatch to remain plausible. That is the danger of silent unit errors. They rarely announce themselves with a dramatic visual signal. They often appear as ordinary data. The broader engineering lesson is that every number should carry its physical identity, not just its value, but its unit, reference frame, time basis, sign convention, and intended use. A force is not an impulse. A mass is not a weight. A distance is not automatically a radius from the center of a planet. Even when two quantities use familiar words, their meanings can differ. A reliable design makes those meanings explicit and difficult to confuse. The case also changes how I think about automation. Automation reduces repetitive work, but it can amplify a bad assumption at machine speed. The software did not invent the unit mismatch, and it did not independently understand the mission. It performed calculations according to the data and rules provided. Human judgment was still needed at the interface, deciding what a field represented, confirming how it was converted, and checking whether the resulting trajectory made physical sense. The answer is not to reject automation. The answer is to automate the right protections. If a conversion is essential, make it visible in the interface. If a parameter is mission critical, make the unit part of the parameter itself. If a result depends on a convention, test that convention with a known reference case. And if two teams exchange data, make the handoff an engineering object that can be verified, not an informal assumption. The Mars Climate Orbiter case is therefore not only about Mars, NASA, or metric units. It is about how modern systems fail at their seams. A spacecraft may be built from thousands of components, but its mission depends on connections between those components. Hardware connects to software. Software connects to procedures. Procedures connect to people. Contractors connect to operators. And every connection needs a shared definition. When those definitions diverge, the system can remain calm, orderly, and apparently normal while moving toward the wrong result. That is what makes this case so useful for engineers, programmers, managers, and anyone who works with technical data. The most important question is not just, what number did we receive? It is, what does this number mean, where did it come from, and how do we know the next system interprets it the same way? If I had to reduce the Mars Climate Orbiter lesson to one sentence, it would be this. A unit is part of the instruction, not decoration around it. The missing conversion was small in code but large in consequence because it entered a chain that depended on precision. And the prevention is equally clear. Define units at every interface, convert them deliberately, test the full data path, and require independent checks before an irreversible mission event. If you found this case useful, like the video, follow for more evidence-based engineering history, and comment with the first unit check you would add to a mission like Mars Climate Orbiter. Sometimes the most important safeguard in a complex system begins with a very simple question. What exactly does this number mean?